If we could have all of the speakers from this session to join us up here on the stage now, we'll take some questions for all of the speakers. While they're moving up, if anybody has a question, if you could move to a microphone. Okay. All right, we've got a question right up front here.
Thank you. Kadambod Siddiq from University of Western Australia. My brief question is to Amelia. You mentioned that the hardpan is broken because of the cracking place. What is the effect of that cracking, particularly around flowering, grain filling time, on the disruption of the root and hence leading to drought and so on?
That's a good question. I also wonder that, especially since my background is root biology, but it's not something we have started studying. I would like to.
A question for Richard. That fascinating talk. You said, I mean, you measured the effect on the soil water content at different depths and was sort of surprised that the soil wasn't wetter. In fact, you said it was even slightly drier and that the amount of hydraulic lift was small. But isn't the fact that the soil isn't wetter, isn't that because you've got much more vegetation, much more transpiration, I assume? I mean, isn't that consuming a lot of water, and that's why the soil doesn't end up wetter as a result of hydraulic lift, because the water is actually being used by greater transpiration?
Sorry, I didn't. Can you repeat just the last bit on the question? I'm having a hard time hearing you, actually.
Okay, you measured the effect of the hydraulic lift on water content in the upper part of the profile, and it wasn't wetter. You said it was actually slightly drier, and commented that the amount of hydraulic lift wasn't very large. But isn't the fact that the soil ends up not wetter but slightly drier, isn't that because a result of greater transpiration because of the greater vegetation that you have now?
Because of the presence of you mean the transpiration from the shrubs or the millet plant?
Both.
Well, the millet plant has been coppiced, so there's no above ground vegetation. So they're really, other than what might be lost on just the bare stem, that wouldn't be part of the equation.
Oh, okay.
Got a question over here.
Okay, Gustavo Sleffer from the University of Lleida. To Victor Sadras, first, thank you for the enlightening talk. My question was, I have two questions related to the QTL for plasticity of yield. The first one is, as you showed before, that plasticity may be good or bad, depending on the condition, whether we should point out to target together QTLs for yield potential and QTLs for plasticity. And the second one, more difficult perhaps, is there are environmental drivers driving plasticity. I know, if you have a gradient of radiation, it may show that some lines, some genotypes are more plastic than others. But then the use of the plasticity should be considered in the context of that driver. If you want to use that plasticity for other drivers, like gradient in temperature, it may not work. So do you think if there is a way we can consider the QTL for plasticity by environmental driver interaction?
Thanks for your questions, Gustavo. Yes, so the hard work is to collect the data. Once you got the data, if we can combine approaches and the approaches agree, we have more confidence in the results. If they don't agree, we can go further and gain insight. So I fully agree that we can combine approaches. So when you have a clear winner, where high plasticity gives you drought adaptation and potential, that's the target trait. So you select, or you try to look at what's driving the plasticity for yield, because you have the win-win combination. But even in that case, it might be with that approach we are missing information. So using a standard approach for QTL per environment, and then using these neat approaches of looking at what environmental factors are driving the G by E, it's useful. So it's not one or the other. I see them as complementary. But your point about what are the actual environmental drivers for plasticity is important. And if you go back to that paper of Anthony Brosho, 1965, he sets half a dozen of principles. And what he says is plasticity is specific for the genotype, so different genotypes have different plasticities. Is specific for the trait, so stomatal conductance might be, seed size is not plastic, but seed number is. And it's specific for the environmental drivers. So you might have a variety that's highly responsive in great number for nitrogen, but it's not, but the plasticity for radiation or temperature is different. So it's, plasticity is dependent on all those things. So having an idea of how yield plasticity relates to water or nitrogen or temperature is important.
Yes, sir, on the left.
Rajendra Ranu from Colorado State, US. My question is for the gentleman from the Ohio State. Fascinating, fantastic piece of work. But in terms of the beneficial organisms, can you say something about what sort of organisms are there? And number two, do these organisms change from one location, I mean to say distance location, from the point of where you have already done research?
Okay. So, yeah, we've investigated the diversity of microorganisms in the rhizosphere of the shrub and the millet plants that grow there. So at this point, we've done a lot with mycorrhizal fungi, and indeed we find that millet plants, besides this possibility of common hyphal network, there are more spores, there are greater infection rates of the millet plant and the peanut plant when it's grown in the presence of the shrub. So the shrub helps the crop plants be better infected with mycorrhizal fungi. In terms of other bacterial or other fungal beneficial microorganisms, we just published a paper using deep sequencing, and indeed we find greater abundance of genera that are known to be beneficial microorganisms. They are harbored in some cases. You find unique ones with a millet plant with the shrub, and they do not exist when you grow that millet plant away from the shrub. So there is evidence that indeed there are beneficial microorganisms that are promoted by the shrub rhizosphere. Whether they do anything or not, we don't know, but we are trying to get funding to really go after bacteria that are known to reduce drought stress. And so that's a whole nother area we'd like to go into, but we don't know if they are part of this equation yet or not. Let's see, what was the second question?
About the
distance.
The change from one distance location?
Right. So if you just compare the soil inside and outside the shrub, there's a big difference. And what the really interesting thing is that if you track the microbial community through the dry season, with the shrub, the microbial diversity is maintained all through the dry season, and compared to outside the shrub. And processes continue, like mineralization of nutrients, continue all through the dry for 9 months, when normally you would expect that in this dry environment, nothing happens after the rain stops. But indeed, because of this hydraulic lift, there are small amounts of nitrate and phosphate that actually build up and then become available for the crops in the spring, which we think is actually, for a low input crop like millet, it actually adds up to be something significant.
Okay, we're running out of time, but Dr. Sharma, a short question, please.
Thank you, Anthony. Dr. Richard, thank you for that wonderful piece of work that you presented here. Finally, at the end of the conference, I'm very happy that we are speaking on microorganisms. So my question here is, that did you see any difference in the total or the available phosphorus in your area? What was the scenario there? And did you see any phosphate solubilizers as you were speaking about the microorganisms? Because I would be happy to know something about that in that area.
Sorry, I missed the total. What did you say the first?
I wish to know about the total and the available phosphorus status. Yeah. And did you find any PSBs or PSMs over there?
Right. So on their first group, Equidosa, our PhD student, went after phosphorus. And indeed, what we find is that below the shrub, phosphorus absorption is reduced. And there's higher levels of phosphate in the rhizosphere of the shrub. So that does assist the phosphorus situation. Was there a second question?
What was the scenario of the total phosphorus and the available phosphorus? Because as we know, it is a log nutrient.
Right. So the phosphorus levels are slightly higher beneath the shrub, but these are, and it depends on where you are. In the north, sandy soil, there's not much of a difference in total phosphorus, but if you go further south, there's more clay, and there indeed you find more accumulation of phosphorus below the shrubs. That's measurable. In the north, on the sandy soil, not so much. But at both locations, you always find more higher levels of phosphate, extractable phosphate, although it's still relatively low.
Thank you so much.
Right.
I think we can take one final question for one of the other speakers that hasn't been questioned already.
Jason DeBrine, DuPont Pioneer, the States. Question for Esteban regarding once this salt moves to the soil surface, does the field ever recover? And if not, I mean, how can you begin to continue that progression into the more arid climates, knowing that you'll eventually cease any production on those types of lands?
I don't have an answer. Fortunately, we are in the early stages of this, but when you go to very dry areas, it takes a lot of time to get there because there's not a lot of water. It is on the wet edge of the semi-arid where we see this happening. And once the water table gets at 1.5, 1 meter of depth, it's very difficult to get out of this situation. And the most common trajectory is to go back to pastures, never back to crops. But I'm very curious about how this process went on in the Indian-Pakistan territory, where this may have happened long ago. One way out is irrigation. And you're all the time dealing with the difficulty of irrigating with salty water. But it seems that's one way out. The other way out could be moving to rice, where you have a flooded situation in which salts are more diluted. In Argentina so far, the only pathway out is pastures.
Okay, unfortunately, we have to end the session here. So we've had a fantastic session, I think, on agronomic management and cropping systems for water-limited environments. I'd like to thank all the speakers, especially the first three speakers who've given us a lot of in-depth knowledge. So a round of applause. I'd like to thank also my co-chair, Stephen Brown, and also the organisers for putting together this session that's broadening out the topic and bringing a lot more agronomy and even some microbiology and some socioeconomics into the frame. So thank you very much.